All right. Hello, everyone. Thank you for being here. It is my great pleasure to welcome Gautam Kamath to UBC and introduce him for this CAIDA talk. So Gautam is an assistant professor at the University of Waterloo and an affiliate at the Vector Institute, where he works on trustworthy and reliable statistics and machine learning. Which include a lot of really good work on data, on privacy-preserving data analysis and differential privacy. Some of this work was actually deployed by the US Census recently, so that's pretty cool. And he's also known, at least to some of you in the room, for putting a lot of great public material out there on differential privacy. And so I'm really excited to hear your talk today, Gautam. So welcome, and please take it away.
Thanks so much, Matthias, for the nice introduction, and thank you also for having me here. I basically just said, hey, I'm planning to drop by, and like next thing I know, he's got this whole thing set up. So thank you to Matthias and also Aaron for help with all the logistics. Appreciate it. Yeah. So today I'm going to tell you about. I do some stuff in sort of on both the theory end and the more applied end. Today, I'm going to give a slightly more applied focused talk on differentially private fine-tuning of language models. This is a joint work with a bunch of amazing collaborators who are primarily based at Microsoft. Actually, Microsoft, including Redmond, the UK, as well as in Beijing, so all across the world, as well as some collaborators at University of Washington and Sun Yat-sen University as well. This is a work that was at iClear this year. And yeah, this is supposed to be a fairly casual talk. So please, if you have any questions, I know some people in this room from talking earlier that people already are very experts in this area. So feel free to ask questions, advanced questions, basic questions, anything I'm happy to take online. Cool. So first of all, let's start off with this XKCD comic you might have seen before. What's going on here? You can see this user is typing into their computer, "Long live the revolution. Our next meeting will be at," and then they ask their email client or whatever this is to complete this sentence. And their whatever model, machine learning model is behind this suggests that appropriate completion would be the docs at midnight on June 28th. So as the caption says, when you train predictive models on input from your user, that can leak information in unexpected ways, which the implication is that something illicit is going on at the docs at midnight on June 28th, which this has leaked that sensitive information belonging to these individuals. So this is a comic, it's a joke, but of course, reality resembles comedy sometimes more often than not. So let me show you how this is actually realistic. This is a work by Carlini et al. So what they did in this work was they first trained an LSTM RNN type model. And what they did was they added a canary phrase to the training data, sometimes multiple times. This is a reference to the term canary in a coal mine, meaning if you can find this phrase, then maybe there's something going on. So they added a phrase which is something like, the random number is 2812655017, a very random seeming number, not something you would expect a machine learning model to spit out unless it somehow memorizes training data. And what they found is that these canary phrases have lower log perplexity scores. So this is a table from their paper where you can see that essentially if you put a lot of phrases like this and try to measure what this is, you'll see that it was more likely to output exactly that same random number. And the ones which are closest were most similar to it. So somehow it seems like it's leaking some information about the training data here. And yeah, that's of course something we'd want to avoid. If say there's a random number, but what if that was a social insurance number or something? Now you might be thinking like LSTMs, what is this, like 2013 or something? Like this is for more modern machine learning models as well, including say GPT-2. There's another work by another Carlini et al. Work, and there's a blog post associated with it. And this is from the blog post. They say that we focus on GPT-2 and find that at least 0.1% of its text generation, conservatively, contain long verbatim strings that are copy-pasted from a document in its training set. And this can be problematic, of course, if this is cases such as personal information or copyrighted content. Here is one of the figures from their paper where they show if you prompt this large machine learning model, GPT-2, with the prefix East Stroudsburg, whatever that's the right thing to do, don't worry about it, but it'll spit out this memorized text from its training data, which they redacted for privacy's sake. But you can see that it's some Peter W.'s personal information. It turns out this appears on some tech report that he put out, and yeah, it has his email, phone number, fax number, which can be problematic. And that's not it. Sometimes it's copyrighted content. They worked also with GPT-3 and found that it was able to reproduce a full page of Harry Potter and the Philosopher's Stone before making a single mistake. So somehow it got hold of this training data and is spitting it out, and it's copyrighted. So that seems pretty bad for privacy for these reasons. Also, maybe you have proprietary data which you're not supposed to leak, which belongs to your users or customers, etc. And it seems like bad news. You'd naturally wonder, are we doomed? And the good news is no, that there's some solutions to this. In the first Carlene et al. Paper, they commented that while early stopping and dropout and traditional regularization type methods were insufficient to prevent this type of memorization, those might be the first things you try to prevent overfitting. They didn't work. However, differentially private machine learning was able to fix the issue completely, albeit at some loss in utility. So I know many of you in this room know what differential privacy is, but just so we're all on the same page, we'll have a couple slides just catching this up. So differential privacy is kind of accepted as, it's a strong and rigorous notion of data privacy. It's adopted by many organizations, including, as Matthias mentioned, the US Census Bureau, also companies like Google, Apple. People like to use the term that's the gold standard for data privacy when it comes to preventing memorization and a whole host of other types of attacks. So in this slide, I'm going to try to give you a picture of what differential privacy tries to prevent against. I'll flash the technical definition, which is a little bit tricky the first couple times you see it, so don't worry if it goes by you. I'll have like the informal definition, which will be good enough for today's talk. So, but at least to try to show you what it means, we imagine the following type of pipeline. We imagine there's some data set X, which is fed into an algorithm M, and that algorithm produces an output. Then we imagine instead that maybe there was a different input fed into the same algorithm, X prime. You'll notice that X and X prime are similar, but they differ in, say, exactly one entry. They're in some sense neighboring, because you can get one from the other just by changing one entry. So now the idea is you have an adversary. If you've ever been to Waterloo, you'll understand why this is the adversary. So you have an adversary who is looking at the output of this algorithm. And what they're trying to do is they're trying to figure out whether the input was X versus X prime, looking solely at the output. And if the adversary is unable to distinguish whether X or X prime was fed into the algorithm as the input, then intuitively speaking, we say that the algorithm is differentially private. So roughly speaking, it's insensitive to changes in exactly one training example. A little bit more formally, like here's the formal definition. If this doesn't make sense, I'll read through it and try to interpret it for you. But if you don't get this, don't worry. We'll be able to continue nonetheless. We say an algorithm M is, say, epsilon delta differentially private if for all inputs X and X prime which differ on one entry, like these two, they're called neighboring. We have the following type of property saying that the distribution over outputs of the algorithm is approximately the same, that the probability of any event is preserved roughly. And a little bit more formally, it's this type of multiplicative and additive guarantee right here. If you've seen differential privacy before, this old hat. If not, it's a little bit weird and we don't have time to get into that. But roughly, I think sticking with this type of intuition that the probability of every event that could happen is approximately preserved is good enough for today. So that's differential privacy. It's just to sort of repeat, it's a rigorous notion of data privacy. And the implication, most importantly, is that if a trained model is differentially private, then it can't depend too heavily on any particular training data point. And again, sticking with this intuition, the model is essentially the same as if your data point was never trained on. So you can see how that's good for preventing memorization, because if there's a secret which is specific to one training point, like my random number is 1, 2, 3, 4, 5, then If it's the same as if that data point wasn't there, then it shouldn't memorize something like that. And as one comment, I'll mention that this is compatible with learning, because when you think about machine learning in the limit, we really don't care about the specific training data. We're trying to learn the underlying distribution. So somehow this might hurt learning in the low data regime, but if you have enough data, really, it shouldn't affect anything in the end. So let me pause here just to see if there's any questions about the definition or, you know, the kind of guarantee we're going for. Cool. Just want to make sure we're all on the same page. So this is talking about just a definition. You might be wondering, how do we make sure our machine learning model is actually differentially private? And fortunately, there's very convenient techniques and tools for that sort of thing. The most common one is differentially private stochastic gradient descent. So first off, I'll flash what stochastic gradient descent usually is worded as, and then we'll see the differences. So SGD is simply you draw a mini batch of data points, compute their gradients, skip step 3 for now, but you average their gradients and you take a step, repeat. So, you know, this is should be hopefully familiar to people who have done machine learning. Take gradients, average them, take a step, repeat. Now, the very convenient thing is that DPSGD, as it's called, differentially private stochastic gradient descent, is a very minor modification of this procedure. All you have to do is you have to clip the per example gradients to an L2 ball, and then you add Gaussian noise to the average. So to give you some idea of the intuition on why that's the right thing to do, remember that I was saying with differential privacy, we want to make sure that no individual point contributes too much to the final model. And a reasonable way to do that is by clipping the gradients, that in case one point has a super huge gradient dragging the solution over in one way, we're going to limit that, making sure that it can't really pull us too far in one direction. And similarly, we're going to add Gaussian noise to try to mask the contribution of any one data point. So yeah, it's essentially the same as SGD, except we just clip and add Gaussian noise. Yeah, you'll see that this is very convenient because it's almost exactly the same as what people do already, which makes it very easy to substitute this in. It's a drop-in replacement for SGD. You know, any model you've trained non-privately, you just drop in a DPSGD, and now magic, with some appropriate accounting, is going to be private. There's a few caveats, but yeah, generally it works. You know, batch normalization issues aside, yeah, this generally works a lot of the time. So this is great. You know, why isn't this what everyone does? Why not train every model privately? Just change it to like this and go on with our lives. There's a few catches here. Catch one, which is probably the biggest one, is accuracy. Differential privacy can be sometimes disastrously bad for accuracy. Let me show you one example. This is a little bit outdated now, actually. There's better things recently, but here is a table of results from this paper by Tremere and Bonnet. Very nice work, where they show for the data set CFAR10, usually one of the easier benchmark data sets for for machine learning in general. Kind of, if you know MNIST, this is the next step up, which is slightly non-trivial. Yep.
Can I ask a question about the previous slide?
Oh, yeah, for sure. Yeah.
Does it matter if you clip before averaging or after averaging?
Yes, you have to clip on a per example basis, and that's important. Just because otherwise you could have individual high sensitivity things which, you know, kind of cancel each other out. And yeah, you do have, but that's an important point, which actually will be part of catch 2. In fact, we'll see. But yeah, so here for CFAR10, this is a common one, kind of, you know, baby's second machine learning problem in image classification. MNIST is the baby's first classification problem. Yeah, and you can see that with differential privacy, the state-of-the-art accuracy, at least when I did this, if you go for epsilon equals 3, which is a pretty strong privacy guarantee, to be fair, you can get 69% accuracy, which is like, you know, you tell this to any machine learning practitioner who's not in privacy, and they'll laugh you out the door. Actually, like, there was a big breakthrough where I think with epsilon equals maybe 7 or 8, they actually managed to get up to 80%. And this is, I think, a really nice result. I saw someone on Twitter commented, like, can you do something besides CFAR 10? And I think they were in good intentions, but I think they're really missing the point that CFAR 10 is surprisingly hard with privacy. Yeah, because like, you know, non-privately, you can get 98, 99%, no problem. And I would think most ML practitioners would think a 30% loss in accuracy, or, you know, another way of seeing it is increasing your error by 30 times is just not, don't even start. It's a non-starter effectively. Yeah, question?
Epsilon BP is increasing, and then the model is more private or not?
Great question. Sorry, I should have clarified this. So yes, differential privacy is a quantitative definition, meaning you know, things can be made more private or less private depending on how you set epsilon. In particular, if something is non-private, then epsilon is equal to infinity. Something perfectly private is epsilon equals 0. So think of this as being more stringent and this as being easier. You'll notice that it should be ideally like monotone. These should be like increasing as you go down. But sometimes the setup or just things being earlier might result in the contrary. But yeah, this is the first line. Think of that as being the strongest privacy guarantees. Great question. Any other questions about accuracy here?
Does it mean it's possible to maintain the model private and more accurate? Because this is not strictly monotonic.
You're asking, so there may be, for example, this was trained with some algorithm which is epsilon equals 3 differentially private. There might be another algorithm or another architecture or some other tricks you can do which would result in it being the same level of privacy but more accuracy. That's possible.
Is there a metric that can measure the privacy and accuracy together?
It's a tough question to answer. I guess like usually the way that we do it is the privacy guarantees have to be proven. Like you basically, before you even run the algorithm, you sit down, pen and paper, and like prove the fact that this is going to be epsilon equals 3 differentially private. And only then after then can you really measure the accuracy. So it's kind of like tough to, they're kind of mismatched because these are provable guarantees. These are measured guarantees, if that makes sense.
Because I was thinking probably one proposed a differential private technique and it has higher private guarantee, but accuracy is lower. And the other one is more private, but always like one is higher privacy, lower accuracy, and other one lower privacy and higher accuracy. How do you compare this?
I see. So maybe like, yeah, how it's sometimes you have to pick which one is better, right? Do you value the accuracy more or privacy more? And I think trying to, maybe another question you're asking is kind of, how do you translate an epsilon guarantee into like what that means to the stakeholders? And this is a very, very difficult question. For example, in the US Census, as one key application, they tried to measure, suppose we set epsilon to be this quantity, what is the monetary impact of what that would have? For example, if it ruins like all the utility that you have, then that would cost too much and you should set epsilon higher. So this is kind of a policy question, which depends on, yeah, the choice of epsilon, I'd say the policy question, which depends on where you're going to use it down the line. That's a very, very good question. Yeah. Anything else? Cool. So the first catch is accuracy, and this is probably the highest order problem. There's other problems, including the fact that, say, the time and space used by differentially private algorithms is often much larger. You know, and in part, this is caused by the issue that we talked about before, where often you want to do per example clipping. You have to do per example clipping really to get the privacy guarantees. And that's not something that modern machine learning things are optimized for. And in some cases, it can cause slowdowns as large as 2 orders of magnitude. So here's a work led by 2 awesome undergrads at the time at Waterloo. And you know, this is comparing, there's one framework which is called JAX, which seems to be very effective. But the top plot here shows that, you know, essentially the overheads for running things privately can be kind of off the charts and much, much bigger than the non-private settings. So kind of the takeaway is that, you know, things can be much slower, as well as often having much higher memory usage. Don't stare at this too hard, but essentially the takeaway is that it can handle much smaller batch sizes compared to the compared to the non-private analogs. So in summary, we have really we have very easy to just plug in methods for differentially private machine learning, but their downsides, their costs, including a huge loss in utility and big resource overheads. So that's what we should, let's put a pin in this for now. Just this should be the takeaway for the moment, and we're going to shift gears a bit and try to tell you what's been going on in the rest of machine learning world in the meantime. And I'm sure many of you know large language models, which are an informal name if you like, or if you're from Stanford, maybe call these foundation models. But yeah, generally this is a sort of catch-all term which is used generally to refer to transformer-based large language models, which this is a figure from this paper of Vaswani et al., hugely influential, called Attention is All You Need. We're not going to discuss too much about the particular architecture here, but this includes models such as BERT, GPT, and a host of other machine learning models, Lambda, and stuff like that. And the thing about how these machine learning models are used is a little bit qualitatively different from the more conventional way of doing machine learning, in the sense that these are typically used in a two-step procedure where, first of all, what you do is you do some sort of pre-training on a large diverse data set, often via self-supervised training. So sort of, just get a lot of data. It doesn't have to be very good quality. It just has to be diverse and very, very large. And then you pre-train. And then what you do after that is you fine-tune some or all of the weights using a smaller task-specific data set. So this is kind of the pre-train then fine-tune paradigm, which has been sweeping the nation in machine learning world. And the nice thing is that this type of two-step paradigm lends itself very nicely to differential privacy, or privacy in general, because let me show you a couple diffs. We can imagine that we do this pre-training on a large, diverse public data set, and then we can do fine-tuning on a small task-specific private data set. So let's go a little bit more in depth on this. So the first step is to pre-train on a large, diverse public data set, where, like I said, even in the non-private setting, these are typically chosen from large, diverse things which are online. For example, downloading the entire text of, say, Project Gutenberg, which is a bunch of old books, downloading a lot of Wikipedia, outgoing links from Reddit, various different sources, of some of dubious quality, but it really, the focus is on getting a lot of diverse data set, a large diverse data set, which is very, very big and has many different types of text. And the key thing I will emphasize here is that maybe the way I should have written this is publicly available for the most part, in the sense that all of this, you with enough time and computation, you can sit on your computer and download this all with a big enough hard drive and get it on your computer. So it's publicly available. That may or may not mean it's actually public. There's some privacy concerns, perhaps. For now, we'll defer this. We'll discuss it a little bit more later. But I'll say at least for now that the cat is out of the bag. If there's any public secrets out there, they're kind of already out in the public. So maybe we can't really prevent them after Pandora's box has already been opened. I'll mention that there's some work on privately training BERT large and T5. So, this stage, we're going to assume that the data is all public. There's some work that treats it as private, like these ones, but that's not really our focus today. Our focus will be more on taking this pre-training as, for granted, and then we will fine-tune privately. But yes, question?
Getting back to the East Strasbourg business. So you said that the fellow whose name was his information was disclosed was from a tech report. So I assume a publicly available tech report. So that would be information that was publicly available and part of this pre-training. So when you say that the cat is out of the bag, then are you saying that okay, it doesn't matter that we disclose this information because it was publicly available anyways?
Yeah, exactly. In fact, if you just Google the redacted version, you can find exactly who it is. I've done this before, and their information is still there. But yeah, so I'm saying that is probably a privacy concern in some way, but at least for now, let's put it aside. But it's something we should, as responsible researchers, be caring about, I think.
So the bigger concern is what happens, I guess, in step 2, when could similar issues arise with non-publicly available data.
Exactly. For example, step 2, we're going to think of this as a smaller task-specific private data set, which could be things, for example, if you're training, say, like a sentence completion thing for emails, it could be your user emails, which are things you do not want to disclose the privacy of. Those are explicitly sensitive and private data. Also, say medical diagnoses or medical text or something like that, which are task/domain specific and also explicitly sensitive. That's kind of what we're going to think about as being perhaps here.
I have two answer questions.
Yeah, please ask.
If I go back to the slide,
For sure.
I'm not a machine learning expert, so I'm wondering, are these two-step procedures, is that only exist in language model or exist in other model like image or something like that?
Good question. Yeah, it's done in all, in not only for text data, but also for image classification problems as well. This is kind of the common way that people do pre-training on, they do pre-training similarly for image data.
Why do you choose language model instead of other model?
Yeah, I think you got to start somewhere is one thing, but like there's other people who've also done the image classification type equivalent of our investigations, and they also work similarly well. I would say chronologically, in terms of these like large language models and foundation models becoming very popular, really language models seem to have kicked off the revolution. People use this paradigm a lot in the past, but like especially in terms of getting huge advances in accuracy, language models was kind of where it became very popular first.
Can your differential privacy technique for language model be used in other model and image like that, or there will be some difference and cannot be totally applied in that kind of model?
Yeah, so spoiling a bit of the hype in the future, like I'm going to say that like we actually don't have any dramatically new method. I'll say that literally just doing DPSGD will be pretty much good enough. Like there's more our findings that this actually works surprisingly well, which I think is the most interesting part. And yeah, that's exactly what people have done for these other things as well. Essentially just pre-training on public data and privately fine-tuning is like, it solves a lot of problems. Cool. Yep, thanks for the questions. Cool. So yeah, like I said, we'll focus on these smaller task-specific private data sets as being like user data, emails, medical data, or so on. Something that you can't really let get out in the public, maybe some proprietary data set you don't want your competitors to have access to. And this is part of kind of a broader agenda of trying to understand when and how much can public data help with private data analysis, and what are like, you know, the boons and the advantages, and what are the pitfalls? This is kind of a question which is on my mind a lot nowadays. And kind of the one of the reasons why it might be helpful is, you know, starting from scratch is really hard. Maybe the transfer property, which is common in machine learning non-privately, could help us. So there's some hiccups that I'll mention, which makes it a little bit tricky. First of all, large language models are, as the name suggests, quite large, with billions or even in some cases trillions of parameters. And they also take a significant amount of memory and time to train and store. So they're not really very portable. These are things we would hopefully like to deal with. This is just in the non-private setting, and things get harder with privacy for other reasons. Like one thing I mentioned is the time and memory overheads. But one thing especially that I think is very interesting, and if you asked me like 2 years ago, I would have told you that you actually want smaller models for differential privacy, and that would be better. I put question marks here because it's a little bit of a lie. There's not a true statement. But the reason why, for any experts in differential privacy, they'll know that the more parameters in a model, the more noise you have to add. And consequently, if you have a big model, you're adding a lot of noise, and therefore you're going to get bad accuracy. And so I would have told you, you have to balance the model capacity with the magnitude of noise. And let me show you some plots maybe to make this a bit more concrete. You can see here, these are some plots from Tremere-Bonnet, and they show, no, sorry, this is from Paperno et al. Actually. And they show that here's some model, yeah, what do I want to say? There's some machine learning model, and you can see the blue lines are the private accuracy and the orange lines are the non-private accuracy. And the x-axis shows as we make the architecture bigger and bigger in terms of number of parameters. So as you go to the right, this has the more filters in one particular layer. And you can see as you make the model kind of bigger in this one specific way, and thus more expressive, then non-privately, the accuracy goes up and up and up for both MNIST and fashion MNIST. But meanwhile, if you use private training, then it'll go up and then it goes down pretty consistently. So it seems like from these examples, and also one by Tremere and Bonnet, where they saw that a larger model actually gets lower accuracy, I would have told you that you have to balance model capacity with the magnitude of noise. So somehow maybe these large models are incompatible with privacy just because of the fact that, you know, with a billion or more parameters, then you're really adding too much noise to get any sort of meaningful signal. You'll probably be over here on this plot is what I would have told you. So these are some problems. And the fortunate thing is, again, in the non-private world, there's been a lot of work on, say, parameter efficient fine tuning. These types of work show that, in fact, perhaps surprisingly, you can get away with tuning less than 1% of the model's parameters of a large language model. Meaning, while I said, you know, you do private fine tuning of the entire model, maybe we can just focus on just a very, very small fraction of those parameters, and that might alleviate some of our concerns. And in the non-private world, it seems like this is very effective, giving comparable accuracy versus tuning 100% of the parameters. Some of the buzzwords you might have heard are there's things like adapters, compactor, LoRa for low rank approximation. And these are just a few of note.
This is non-private.
Non-private, yeah, this is all introduced in the non-private world. I'll give you one example. I have some slides on like 2 of them, but just to show you the gist of how these sorts of things work. Here's adapters. So you can see here, what do I want to say? So this is the transformer architecture for the most part. The only changes are you add in here this adapter layer and this adapter layer. The adapter layer, if you zoom in, it looks like this. So the idea is you keep like all the other layers frozen. So that is the feed forward layer is frozen. These feed forward layers are frozen. But then you add in these new layers and you only tune parameters in these layers and these layer norms. So the effect of this is actually you're only going to have 1% of the parameters which are being fine-tuned rather than everything. So this kind of decreases the dimensionality of the parameter vector by 2 orders of magnitude, which may require you to induce less noise into the model for privacy. Questions about adapters or like how? Yep.
So these are new parameters that you have. It's not like a selection of parameters that you freeze that were already trained.
Indeed. For it varies by technique, from technique to technique, but for adapters in particular, they're very nice because yeah, they're literally new parameters you plug in, which you don't touch any of the old parameters except for the layer norms, I guess, the norm parameters. Yeah, Matthias?
Do you actually train them on the training data first as well, or you start them first?
You start, I think you typically start these from scratch in the sense that there's one setting of these parameters which just has to be the identity transformation. So like it'll be the exact same thing. You have a specific initialization, I think, generally. But yeah, you don't put them in during the pre-training stage, only during fine-tuning. Yep.
So in this new mechanism, is the accuracy still related to the number of parameters or not?
When doing private fine-tuning?
Yes, because you mentioned that frequently, if you find that this larger model, you apply P, accuracy will decrease more. When this model, with the adapter model, or adapter mechanism, and then related to the number of parameters sometimes. Or still have that kind of.
Yeah, that's like you're stealing all of my suspense. But yeah, in the end, we'll see that in fact it doesn't really matter all that much in the sense that bigger models will nonetheless be effective with privacy, which is contrary to what I would have told you like a year and a half ago. So that's I think a surprising finding. But we'll return to this. Cool. So hopefully, you get the idea of how one of these parameter efficient methods works. There's more advanced things like compactor. Maybe I'll show this where this is a specific benchmark, and the base accuracy is 60, or the base score that has a 61.76. And by fine-tuning less than 0.1% of the parameters, you can actually get 64, which is a higher score. Like somehow you don't really need to touch most of the parameters, almost any of the parameters, to do really well. So that's kind of cool. That parameter efficiency in the non-private world seems to be pretty good. There's another one called LoRa, which we found to be the most effective. I'm not going to go too much into this. It's kind of similar, Yeah, basically only make low rank updates to any parameter matrix. To answer a previous question of yours, in the sense that before you added in new parameters, now we're looking at the diffs to the current parameters. But let's skip that. The bigger picture is generally going to be, we're going to let this be a pre-trained model, where WPT are the pre-trained weights and X is some input. The fine-tuned model is going to be something with some new parameters data, where the dimensionality of the new parameters hopefully will be much, much smaller than the dimensionality of the pre-trained weights. So the idea is hopefully we can do fine-tuning in a way that will touch far fewer parameters, because hopefully that'll help with some of the dimensionality. And that encompasses all the above methods and other things: prefix tuning, prompt tuning, plug-and-play language models, and more. There's a lot of things which kind of follow this type of framework. So to try to illustrate, just so that's incredibly clear as to how exactly we are going to use these models, again, we can think of it as a 2 or 3 step procedure in terms of how they can be used. So the first step is essentially as you do it in the non-private setting, where you have a large public data set, you use a non-private optimizer, you train some model. Then the second step is to fine-tune it with differential privacy. So everything inside of these dotted lines is going to be not visible to the accuracy, or to the adversary. You can see that this is a smaller private data set, and we're going to use a private optimizer. And what we're going to do is we're going to fine-tune the model, possibly these new parameters. And then after we do this DP fine-tuning, then in fact, a property of differential privacy says you can just reuse these parameters, you can release them publicly, and anyone can use them. So you can just take them out of this enclave, which is only visible to the data curator, and then sort of plug them in and give them away, and anyone can use this smaller number of parameters non-privately. So questions about this type of 2 or 3 step framework, depending on how you view it.
So the large language model parameters are frozen during the.
Yeah, exactly. Yeah, the idea is that ideally we'd only like to touch a small number of parameters, either new parameters or updates to the old parameters, which are low rank or somehow small.
Also in this DP doing procedure, what's the neighboring definition? Is it sentence level?
Great question. Yeah, because like when you're doing differential privacy, you talk about neighboring data sets. Is it involving, say, just like changing one sentence, or maybe a user has many sentences and you add or remove all of them? It's up to, I think, the data curator for the specific application, which one is the appropriate one. I think in our experiments, we did like based on the sort of benchmarks we used, we just did one sentence. But you can imagine for other settings or other, say, federated settings, maybe it makes sense to do something different. Yep.
When you say small private data set, how small can it be? Can it be like 1 data point?
Yeah. So like that's a good question. Like, can you do with like 1 or even 0 data points? In some cases, like this ties into non-private learning in the sense that often you can do 0-shot learning, which requires 0 task-specific data points. And in fact, in those cases, you get perfect privacy, epsilon equals 0. So, and you don't even have to do anything, just skip the middle step, really, go straight from 1 to 3. So, of course, you'll get better accuracy the bigger the small private data set is, but sometimes you can do it with 1 or even 0 examples, I guess, right?
I guess the question is, like, if you have 1 data point, you will have privacy.
I would say if you were given the choice between 1 data point and 0 data points, I would probably just like skip the middle step entirely and go with 0 data points, just because, yeah, because you're going to be introducing noise when you try to fine tune on 1 data point. So it's probably not going to help you much or at all.
Well, every 1 element data set is a neighbor of any other.
Exactly.
So you can't learn it.
Right. That's another way of saying the same. Yeah. Essentially, like you'd have to add noise to mask the contribution of that 1 point. And so, it's it will give you a minor amount of like signal in the right direction, but it's not going to help in practice. I can almost guarantee it'll be like local differential privacy, which is usually you need like much more data to do anything meaningful. Yeah.
What about similarities between the small data set and large data set? If you have two identical things, one in the private data set, the other large data set is going to be a problem.
That is a pitfall. Yes, that is a very good question. What if there's overlap between your private data set and your public data set? And that's when it gets a little bit tricky, because sometimes, you know, what, like I think you said a twin, right? Yeah. What if you have an identical twin and they give their data to the public data set and yours is private? Well, somehow they're leaking your secrets. It can get a little bit tricky sometimes. And there might be some mismatches sometimes between what people intuitively think of differential privacy, or what people intuitively think of privacy, and what differential privacy can guarantee. So yeah, that's one pitfall that anyone has to be careful about when actually deploying these types of things. Yes. Cool. So let me tell you the main findings. So there's kind of two main findings. The first one is that we find that large language models can indeed be fine-tuned privately with quite high accuracy. In the sense, there's a lot of numbers here, but let me tell you the first row. That is fine-tuning without differential privacy. And you can see there's a lot of numbers, but maybe just for simplicity, this isn't always the best comparison, but let's just take a look at the average of these tasks. And you can see that without differential privacy, you can get 93.4 accuracy on these tasks. And taking a look at the last row, this is using LoRa and differential privacy. And you can see that you can get 90.3% accuracy on this. And for those who know some of the lingo, this is on Roberta Large with epsilon equals 6.7. And the kind of cool thing here is the fact that this is only a 3% difference from non-private to private, which is a far cry from like the 30% accuracy drop. It's an incomparable task, of course, but you can see that in that case, it totally trashed the utility of the model. Whereas this, I think some NLP folks would still turn up their noses at this result, but I think it's a lot better than before. Only 3% is maybe a bit more manageable. And it only tunes 1% of the parameters per task. So one natural question based on what I've told you is, did this parameter efficiency really help us? And based on our experiments, we thought so, but I'll mention a very nice concurrent work, actually. The two works were simultaneously submitted to iClear, by this one by Lee et al., which is, I think, it's cool that they were working on the same stuff, but at the same time, they did almost identical experiments as us, actually, in many cases. But they actually showed that full fine-tuning is also essentially comparable. Yeah, essentially, maybe this parameter efficiency was a little bit of a red herring. It has other benefits besides just accuracy, but they found by full fine-tuning, you can get very comparable numbers to all of these. It depends on which task you look at. Say they did better for QQP, we got a bit better for MNLI, but roughly in the same ballpark. Yeah, we got some kind of worse results in this area, and it turned out to be some issues with mixed precision training, which seems to be maybe some framework issues that we're looking into a little bit more. But I'll still maintain that parameter efficient methods still maintain the non-private benefits. So to summarize the first takeaway, it seems like we now have differential privacy for some of these tasks, and it maintains most of the accuracy from the non-private setting. I'll pause here in case there's any questions about this.
So what's more?
Oh, this is a parameter in LoRa, like what rank we used for certain low rank approximations. Yes?
But it says that for compactor, the trained parameter is only 0.053%, much smaller than LoRa. And for LoRa, the average accuracy only improved 5.8. But they use less, much less trained parameters. How would you explain that?
I guess, yeah, sometimes maybe you're going to yeah, it just seems like sometimes some things can be more parameter efficient and save more parameters, but you get some hidden accuracy. I guess it really depends to choose which one based on your setting. Maybe parameter efficiency is really, really important in the sense that maybe you want to deploy this model on a very on a device where it's hard to communicate with. So like you don't want to send them very much data. So maybe in that case, you'd prefer compactor, even though it's a bit less in terms of parameters. Sorry, it's much less in parameters, but it's a bit less accuracy. So yeah, it's trade-offs. Yeah.
Do you have any numbers showing without even tuning? I mean, DP tuning or non-DP tuning, how much accuracy we can get?
Oh, without doing it at all? Like zero shot, essentially.
Yes, just how much it's.
I don't have numbers for that. I don't think it's very good just because of the way that these things are often trained, in the sense that, you know, you do the pre-training without any specific task in mind. And then in the end, for these things, it's like a classification problem. So there's no, you're kind of introducing an entirely new last layer, and you have to fine tune those weights. Otherwise, they're just random numbers, essentially. You have to do something in some sense. Except if you're doing zero shot in a slightly different setting. But at least for this setup here, like Roberta would not do well on that type of thing, to my understanding. Cool. I'll also mention these are for like classification tasks, but also for natural language generation tasks. We have, you know, qualitatively similar results as a big table. I'll leave it for 5-10 seconds, but don't need to worry about it too much. Maybe I'll just say that, you know, the bottom 3 rows are without privacy. The top 4 rows are with privacy. In this case, yeah, for most of these, bigger numbers are better, except for this one where smaller numbers are better. But you can see that the numbers really don't change all that much, qualitatively speaking. But okay, so the takeaway is maybe that it kind of works. But I think the more interesting finding is actually, this surprised me a lot, where we found that bigger models are better, in the sense that, what do I have here in text? Yeah, okay, let's just focus on this. So there are 2 models here. The top one corresponds to Roberta base, and the bottom one corresponds to Roberta large. So as the name suggests, this is a bigger model and has more parameters. So there's 2 things I want you to pay attention to here. The first thing is that the accuracy with differential privacy is higher for the bigger model. So you can see here, privately fine-tuning it gives you 90.3% accuracy, compares to here, which is 87.2% accuracy. The second thing I want you to notice is that the drop due to privacy is also better, in the sense that the bigger model has a 3.1% decrease in accuracy, where this one has a 4.6% decrease in accuracy. So to repeat that, the bigger model is better both in terms of absolute accuracy, as well as the cost you pay due to privacy. And I find that a bit surprising. You know, anyone in the non-private world would be like, they know this very well, that bigger models seem to be a lot better a lot of the time. But again, this is contrary to what I would have told you a year and a half ago, where it seemed like bigger models were potentially worse. Yeah.
You may observe the same thing with food, like isn't an effect of more spatial low parameter?
No, that even with the full fine tuning, that's the same effect as well. Yeah, Danica.
So the difference in the percentages is bigger for the smaller model, but if you look at it as error rates, in both cases, it's like 50% more.
Right.
I just did the.
I was.
It's like 56 versus 45%, so it still is bigger from that point of view, but it's maybe if you think of it as like increase in the Bayes error, we don't know, you know, the excess error, in the excess error, because we don't know the Bayes error, maybe in like percentage increase in excess error, maybe it's actually more.
Right. I see what you mean. Yeah. Okay, maybe like I'll weaken my previous statement in the sense that at least the absolute numbers are definitely better. The absolute drop is smaller, but yeah, you are right that maybe the relative change could be more interesting and the appropriate thing to look at. Yeah.
So I see that the train parameter fraction is the same for both. Do you consider it as almost like a hyperparameter that you can tune? And is it like the optimal fraction?
Yeah. So yes. This R, which I've sort of hinted at, but not really said too much about, that is essentially a hyperparameter of the model. And we tried a few different ones and found this hyperparameter was kind of the best for this.
And is it a coincidence?
we might have selected it for one of them and just kept it and transferred it to the other one. We might not have tried it, but I don't think it was super sensitive to that particular hyperparameter. Yes?
In this process, is the bigger models referring to the retraining phase or the fine-tuning model?
Both. It's really the architecture. You're always going to have a base architecture, and we're just saying like in the Roberta base is like this big, and Roberta large is going to be bigger, you know. So, and you're going to keep it for all the stages.
So both the pre-trained and the fine-tuned weights, the number of pre-trained and fine-tuned weights are increasing.
Yes, correct.
So is there a possibility like because the larger model has better embeddings in the pre-trained stage, so at the beginning of fine-tuning already has a better accuracy?
Yeah, I think that's kind of maybe the right hypothesis, saying that you had this bigger model to start with, so it learned more during the pre-training stage, and it preserves that when you proceed. I think that's probably the most reasonable hypothesis. Yeah. Yep.
Is there any overlap between the retrained data sets and these task-specific data sets?
I think that's a really good question. My understanding is in the non-private setting, people also care about that and try to measure overlap and try to make sure they're not overlapping, because otherwise you're cheating on your test data set. So I think at the same level as that, yeah, we kind of went with the same thing. But it is still nonetheless possible that there's some overlaps, which would be, of course, another privacy violation. But yeah.
I just feel like it would really weaken what DP is doing for you here, right?
For sure. It would make the like a vacuous guarantee for some of the examples, yes. Right. But to the best of our knowledge, there's limited or no overlap. But yeah, at least this is used the way that they typically use it. So it's always possible. Yeah, question?
Could you explain intuitively why your technique understands others' work is aspect? I mean, why their model cannot achieve like bigger models are better? In their work, the bigger models are worse, but what makes special for this work that makes it bigger models are better? Very like intuitive thing.
I think it's impossible to say anything for sure in deep learning, but I feel like Xiaoyue's like suggestion about maybe it learns the pre-training better. That might be the best thing. Like you know, maybe take a big enough model to really learn everything during the pre-training as well as it can, and then that outweighs the noise you add later on.
I mean, why your technique can address this problem, so it may provide insights for other people. Like I want to address some problems, so I can approach the problem after. Like what special probably technique, your technique that can address limitation.
Yeah, I don't think we actually really did too much that special in the sense we did pre-training and private fine-tuning. We did some stuff with LoRa, but it seems like it's not really necessary. So I don't think it's really any magic that we did. It just seems to be a fact of nature that this kind of works.
So I think maybe one point that's missing is that when it was the case that more parameters was worse, it was for training from scratch.
Yes, that's an important.
And so it might be that it's very hard to learn larger models from scratch, or that we don't know how to do it yet. But if you start from a good model, you can fine tune private use. It might be easier, and so you can do it at larger.
So it's not entirely surprising because the comparisons are not that.
Exactly. It's not like a apples and apples comparison, but maybe it's possible that parameter efficiency is still significant in the non-private case and not in the, or sorry, in the case without pre-training, but in the case with pre-training, maybe bigger models are better. I don't know. There's been some interesting recent work by a DeepMind group, which maybe suggests that like bigger models, even in the place without pre-training, can also be better.
That's what image classification.
Yeah, for image classification. So it's like always a little bit different here and there, but yeah, basically I'm maximally confused about how much parameter efficiency really matters or not. It's very unclear to me. Yeah, great questions. I'll mention there's like you can stare at these numbers, but again, it's similar things for net language generation in terms of the accuracy. But yeah, the sort of takeaway that I want to get here is that maybe they'll have better absolute error and less absolute drop due to privacy. The third kind of finding is these can be faster and more memory efficient, but this is, I'll skip this to talk about maybe the bigger pictures, which, you know, what are some of the takeaways? It seems like public data can surmount the deficiencies of private data analysis just by maybe giving some better priors of what the data looks like. And the way I like to say it is that maybe private NLP without public data is like pretending that the English language itself is private information. Like whenever you read a new document, it's not like you forget everything you ever learned about English. You know things about like grammar, syntax, and so some things like that. So you can maybe think of the public pre-training as learning English, and this private fine-tuning is doing something more specific for the setting that you care about. So maybe one could argue that some sort of public pre-training is necessary to make the model learn English or whatever other language you're trying to learn. Yeah, public data can dramatically improve accuracy in private ML, and it seems like also revision tasks. Here's a plot from Tremere and Bonnet. There's also been other dramatic demonstrations of specific phenomena for image classification as well, which I won't get into today. I'll say that this is underexplored, but I think there's been a lot of nice exploration recently. I just want to, because I've hinted at this, I want to mention some of the caveats, which we won't have much time to discuss right now, but we can talk more about this later offline. You might be wondering, is this public data really public? Like, I mean, for example, that Harry Potter book, which was spit out by GPT-3. If you Google it, you can find the text of Harry Potter online. It's still copyrighted, so this is not really kosher to do. Like, publicly available is not always synonymous with public data. And there's also the question of, did we actually learn something from the private data? Does this actually work? Like, we were looking at standard benchmarks which were not privacy sensitive, and the same is also true for like ImageNet, CFAR10. These are not really privacy sensitive tasks. Like what a dog looks like is not something that we want to hide or make sure people don't understand. In particular, these are things like very similar distributions. So if you pre-train on one and you fine-tune on the other, then it's not really doing anything new. It's not learning much new there. And I think there's a big question for the community: what are the right benchmarks for private ML? And just as I think this is pretty much my last slide, I think still this parameter efficiency is a big question. I used to think more parameters means more noise, means worse accuracy. But it seems like often larger language models do better in the end by some absolute metrics, even with full fine-tuning. So I like to ask, are large language models actually small? Maybe this picture I showed, maybe large language models are right here. We're still on the way up, and then we haven't reached the 10 quadrillion parameter models, which would start taking us over the top. So I don't really know. Maybe style of architecture seem to matter. But yeah, this is really a question that I don't have a good answer for. So if anyone here can explain to me the same question, which many of you have asked here, like why do we overcome this this hill here, or why do we land on the left side, is I think a big question, and I'd be curious to know an answer. So in conclusion, large language models can be fine-tuned privately, and utility is actually surprisingly good. And I think there's a sort of paradigm shift over the last few years by works like in this area, which seems to suggest that while before private machine learning seemed to be unusable in a variety of settings, but this seems to suggest that maybe using public data can surmount these issues. I put the star next to public data since this is like an interesting question. I have some thoughts which I'm trying to get down in a position paper that I'm working on with Florian Tremere and Nick Carlini. Hopefully in the next couple of weeks it'll be out. And I think understanding what are the limitations and limits of public data and private machine learning is a very interesting question. So I'll conclude here. Thank you. So we're a bit over time. I don't know. I'm happy to stick around as long as people have questions, but
yeah, I think it's great questions. I don't think we're in a rush for lunch.
Cool. Yeah, Victor.
Just a quick question. So it seems that public data helps, but it's still weird to think that we need public data to be kind of useful in our world. Because it seems that right now we cannot do good models that are only trained with private data. Do you have any hunches or opinions if actually is any possibility that we cannot have good models that are just training on term data, that some data is actually required, or just a matter of we didn't find a good way to use the private data yet?
I think, yeah, the question is like the necessity of public data. I think, okay, first of all, you never need public data, because if you had enough data, enough private data, then you'd be able to, in the limit, approach the right answer. The only problem is the fact that we don't necessarily have enough data. Yeah, there's this paper by Tremere and Bonnet that I've mentioned. They have a great title which says differentially private learning needs better features or much more data. So I think, much more data is one solution. The other is better features, which you can obtain by public data. And I think especially that's like clear why that's useful via the metaphor I gave that, if you don't use any public data for language modeling, then it's kind of like assuming that English itself is a private language, which, is perhaps handicapping yourself a little bit.
I'm a little bit puzzled about the Harry Potter example. I feel like if I Google Harry Potter, I can probably find more than one copy of the textbook.
Yeah.
So if the same data points in the training set multiple times, does differential privacy do anything with that? Or does it say like I can take one of those out and still overfit on the book instead of an entire page?
So yeah, two things. Yeah, it's first of all available online in multiple places, I guess. I guess all of them are potentially illegal. I assume. I'm not sure if J.K. Rowling's gonna go after them, but yeah. But on the other hand, like a nice property of differential privacy is while it's worded for like neighboring data sets, it's not too hard to show that if things differ by 2 entries, then also it'll help. So in other words, like it'll prevent secrets from being memorized from any one thing, but also 2 things. It'll still prevent memorization of that same secret, and 3 times it'll prevent it, but a bit less each time. It sort of smoothly interpolates. If something appears, say, 1,000 times, it'll still be sort of memorized, but less than if there was no privacy. That make sense? Yep. Yeah, which layers to fine tune? This is a good question. I don't think I have a good answer to it. I know there's one paper by students by Fei Li's group, which was in CVPR this past year, maybe 2022, 21, I can't remember. And they show that like they I think give guidance on which types of layers you should freeze and which ones you shouldn't. Have you seen this paper before? Maybe I'll show it to you later. Yeah. So they give certain intuitions, like I think the normalization layers seem often to be some of the most important ones to fine tune. But yeah, I don't personally have any good intuition. Yeah. Right. Let me just go back to DPSGD because I totally 100% agree with you. The fact that this feels like such a weird way of guaranteeing privacy. Like the fact that every single step of gradient descent you have to privatize individually. It's surprising to me that this actually works at all. Like this paper, kind of the big finding of this Abadi et al. Paper from 2016 is surprisingly, if you do your accounting right and all these things, it can actually be good. So there is the question of whether there's a different algorithm that would work to privately train models, but this seems to be very, very difficult to come up with. There's some like, yeah, you know, it would be nice. Here's a hopeful algorithm, which is not private just by itself. Like maybe you train the model and then you get some parameters and then you just noise that resulting set of parameters. And maybe that would be private. That's called output perturbation. Unfortunately, that by itself is not private, or at least no one's been able to analyze it as private, just due to the complexities of deep networks. So I would love to see a better algorithm, but this is the only one that people have been able to conclusively say is private. Yeah, at least for deep nets. I'll say things like output perturbation and what's known as objective perturbation, where you add noise to the loss function. Those do work for, say, convex models and related things. But yeah, for deep nets, open. Yeah.
I guess I'm wondering where you're going with the benchmark idea. So would you actually test the privacy of these networks? Like you had an example at the beginning with that string, like a random number, it's such and such, right? And then whether it would memorize that. Is that something you test, or we just assume the guarantee mathematically?
Right. The nice thing about privacy is that, like, yeah, once you prove it, you know that it will hold as long as you implement everything correctly. For example, there was one paper where they proved something with a very strong privacy guarantee, but then maybe like a week later, there were other folks who did auditing on that and found, okay, the proof had a bug in it, and they actually demonstrated empirically that it did not hold. So yeah, if your proof is correct, then you don't have to do anything else. But nonetheless, kind of as sort of this quote says, they essentially used differential privacy and empirically found that the same phenomenon that they saw here does not hold if you do differential privacy, unless you use a huge number of repetitions of the same phrase that override the privacy definition.
Good. Well, thank you, Gautam. Let's thank him again.
Thank you very much. I'm really impressed by all the questions. These are really thoughtful and insightful.